class, welcome back to multivariable calculus. In this lecture, we are going to learn about line integrals. So typically with integration in the past, as you've been practicing it, we've been in two dimensions in single variable calculus, we have been integrating between an interval under a curve. Now, with line integrals, what we're going to be doing is we're going to be integrating over a curve through a field. So line integrals were invented in the early 19th century to solve problems involving fluid flow, forces, electricity, and magnetism. So if you think about a body of water, say a river, and there's going to be a current, and we map out a path we want to travel through the river. Well, the amount of energy or work that it takes for us to move through that curve that we denote as a function of time is dependent on the direction of the current. So if we're moving with the current, it's going to help us. If we're moving against the current, it's going to hurt us, and it's going to take more energy on our part to move along that curve. And so the same thing goes with a force field, an electric field, a magnetic field. So with line integrals, we start with a plane curve denoted by C, given by parametric equations, or equivalently a vector form. So let's look at some parametric equations. So for example, x is a function of time. Y is a function of time. And we're on some time interval now. This is the key difference here. Not necessarily just an interval in space. This is an interval in time. And of course, the two are related. So the equivalent to this would be a vector equation. So let's look at the position vector. So remember, the position vector is r. Oh no, what just happened? Hold on, let me just erase that. All right, r of t, so that's a function of time, is going to be your parametric equation in the x direction. So that there's our I hat, and in the y direction. So we're just looking in two dimensions here in space. And let's assume that we're going along C, a smooth curve. Okay, so let's look at a graphical representation of this. All right, so we have y versus x. And I am just going to draw a random smooth curve here that we want to travel along. Okay, so there's our curve. And let's say the length of the curve is covered, where we want to travel the length of the curve over some time interval from A to B. And so I'm going to denote my time interval in green down here. So this is going to be my timeline. So this is t, and we're going to go from time A to time B. So let's say at time A, that's going to be my initial position. That's where I'm starting. And so this is my starting point. And let's say then that there's going to be a current, and the current is going to be going off in this direction. So my vectors here are going to be my current, or my force field. So that's what's in purple here. Okay, and so ultimately we're going to be traveling something that's going to be in between the two. So the dot product between our force field and our direction that we're trying to travel. And so this is going to be our field at our initial position. And our initial position will be denoted by P naught. So that's at time A. And so then we move forward into the next time increment. Let's just put it up here so we don't get too smushy. And then let's say that our force field is over here, just for example. And this is going to be P1. 0.1, and so that is going to be, say, here. And P1 is going to be our position vector at time 1. So this was time 0, then time 1. So it's going to be x at t equals 1 and y at t equals 1. Right, and so in other words, this right here is r at time 1, r of 1. Okay, and so then if we move forward in time again, say P2 is over here. Okay, and we'll have our vector. And let's say P3 is over here. We have our vector. Oops. Trying to make them all about the same length. Then we'll go to some, so let's skip ahead a little. And now let's say this would be denoted our P sub I, so some time interval, minus 1. And this is whatever P sub I we're looking at. And then we'll, of course, have our force field or our current. Okay. And then we just keep moving forward in time. So the next one after P sub I would be P sub I plus 1. I'm just trying to make it generic here. And then we get all the way to, say, P sub n. And so the one before P sub n would be P sub n minus 1. And that's the number of increments you have from A to B, right? So we're looking at the definition. We're not looking at infinitesimally small increments here. We're just looking at, so we're trying to get at the definition of this. And so I'd like you to stop and think for a minute, looking at our force field or our current and the path, the curve along which we're trying to travel. So at which point do you think it would be easiest to travel? So think about it for a second. And hopefully you came up with this P sub I minus 1 point. So this is just random here, but what you see is the force is pointing in the same direction as our direction of travel. Now, if we reversed our direction of travel and tried to travel along the curve in the opposite direction, that would be the point at which we're going against the field the strongest, and that would be the most difficult to travel. So we'd be moving much slower, or to keep up the same rate of motion, we would have to use more energy. Okay, so now just keep in mind that the dot product measures the extent to which two vectors point in the same direction. So we get positive values for dot product if the angle is between 0 and pi over 2. Okay, so traveling in this direction here, we're having, with maybe the exception of P2, they're pointing in the same direction of travel. So there'd be a positive dot product. So let's look at the formal definition now of a line integral. So by definition, we're integrating And now we have a C down here, which denotes that we're integrating along a curve of some force field dotted with, or some field, doesn't have to be a force field, I'm just used to that because of physics, dotted with your position vector, or the incremental, like a small little change in position you can think of it of. And so by formal definition, it's going to be the limit as the magnitude of our differences in position, each one. So those increments, those are these size increments here along this timeline of as those increments approach 0. So as you get closer and closer and closer together, as you're used to with the definitions involved in integration, of the sum of I equals 0 to n minus 1 of our field evaluated at our position, so for each increment, dotted with the size of our interval. Now remember, the integration symbol is a long S for sum, so it's a sum for continuous variables. So then we have our discrete sum or Riemann sum here. They're big sum operators for discrete variables. Now in summary then, in words, a line integral is a limit of sums of dot products of the vector field with path elements. Which is exactly what we set up above. Now let's look at a little exercise here. So we're going to let n equal 4. We're going to write the right-hand side of the above equation in expanded form. Okay, just let's practice doing sums for a minute. Okay, so the limit, okay, as we approach 0 of then the sum, which is going to be f evaluated at, so actually let's just erase the limit. So let's just write this out in expanded form. So this inside part. All right, so it's going to be f at our initial position, so the field at our initial position, dotted with the size of our increment, so the distance we're moving, plus the field evaluated at position at time 1, dotted with our distance increment, plus f at our second position, dotted with our increment again. And then finally, at our third position, right? Because n equals 4 here. And so we always start at our initial position, which is at time 0, because we're going up to n minus 1. So n is 4. So we're going, our max n here is going to be, n minus 1 is going to be 3. Okay. So now, before we actually get into line integral, or into the definition of work, I want you to think of something else first. So we'll come back to this. So let's just let our field have P I hat component plus Q J hat component plus R K hat component. And this is going to be a this field is going to be continuous on R cubed. So along a curve, particle will move approximately in the direction t, capital T as a function of time, and this is going to be the unit tangent vector at the position. So if we were looking at a curve and we have our initial position, R naught, and our final position, Rn, then if we looked zoomed in on some R sub I, so some position at some time, and we have, say, our field is almost, let's just say we have a field that is almost perpendicular here. Then the path of motion is going to be this unit tangent to the 2. So it's the unit tangent to the vector at the position. So it'll be like that. And that'll be the path of motion. Okay? So I'm going to erase this so we can get into our definition of work now. And so this is something that you're hopefully familiar with in physics. So just think about work as being force times displacement. So now let's look at work, the formal definition here. So work is going to be the line integral of our field, which is a function of space, x, y, and z, dotted with our unit tangent as a function of space, dr, which can be rewritten as the integral, the line integral of the field dotted with t dr. And remember, this dr is position. So work is a line integral with respect to the arc length of the tangential component of the force. So looking back at this tangential component, t is going to be equal to the first derivative of our position function as a function of time, and then we're going to divide by the magnitude of that derivative with the function of time, And so that gives us that work is going to be evaluated over the interval from A to B, where we have our field as a function of position dotted with R prime T dt. So we've just rewritten the above using T is equal, using our definition of the unit tangent to rewrite work as a function of time rather than position. That's all we did here. So we're converting from position to time. And this is often abbreviated as the integral over C of f dot dr. Okay, so these are equivalent. And this is what probably, hopefully, looks familiar to you. This is the formal definition of work. Force dotted with change in position is work, the integral of that. All right, so now let us try an exercise, another one. So what we're going to do is we're going to find the work done by the force field f of x and y is equal to x squared I hat minus xy j hat in moving a particle along the quarter circle given by the parametric equation r of t is cosine t I hat plus sine t j hat for the interval of 0 is less than or equal to t is less than or equal to pi over 2. So if we were just going to do a little plot of this, y versus x, so we're going to have our quarter circle. And then our field, which is going to be x squared I hat minus xy j hat, is going to look something like this. It's going to start out really kind of, it's going to be pretty tiny down here, and it's going to get stronger as we move away from, as we get more positive. It's going to be something like this. So pretty tiny here. All right, so you kind of get the general gist. So there's our field. And we want to know then as we move in this direction, what the work done by the force, what the work done is. Okay, and moving a particle, okay, so how much work does it take to move along this curve? And just by looking at it, I'd like you to try to determine whether it's going to be positive or negative. So the work done by the force field, okay, and moving in this direction. Okay, so think about it. Hopefully you've come up with some kind of inkling, and now we're going to go through this and let's see how you did. So let's write out our x in terms of t. So x is going to be cosine t, given here. Y is sine t. Dx is going to be the derivative here. So it's going to be minus sine t dt. Dy is going to be cosine t dt. So now let's rewrite our field function as a function of time. So this is going to be f of r is going to be, our x is cosine t, so it's going to be cosine squared t I hat minus, and then our x again is cosine t. Our y is sine t j hat. Okay, so now we've just rewritten this as a function of time. And so our derivative of the position vector is going to be equal to minus sine t I hat plus cosine t j hat. Now we need to compute the work. So work is going to be, from our definition on the previous sheet, the integral over the line integral of f dotted with dr. Okay, and our time interval here is going to be 0 to pi over 2, since we're integrating with respect to time. And then we're going to plug in, so if you look at our definition here, this is equal to, over our time interval from a to b, f as a function of t dotted with our first derivative of position. So let's write that in. So it's going to be f of r dotted with r prime t dt. Okay, so I'm going to have to get a new slide going. Okay, so now writing this in, we're still integrating from 0 to pi over 2. And we're going to do, we have to dot now f with our first derivative. So it's going to be cosine squared t times minus sine t. Okay, so we have to multiply the I components and add them to the j components multiplied together. So this is going to be minus cosine squared t sine t. And then we're going to have to look at the j hat component, the y component. That's going to be cosine t sine t times cosine t. So that's going to be, and there's a minus sign in there. So that's going to be minus cosine squared t sine t dt. So this is going to be simplified as minus 2 cosine squared t sine t. Okay, just adding these together. All right, so now in order to evaluate this, let's do a u sub. So let's let u be cosine t. And so du is going to be minus sine t dt. And dt then, if we solve for it, it's going to be du over minus sine t. Okay, so going back, this is going to be the integral 0 to pi over 2 of minus 2 u squared sine t du over minus sine t, which is going to be, inside our integral, is going to be 2u squared du. So if we integrate that, we get 2u cubed over 3 from 0 to pi over 2, which we'll just leave for a sec since we haven't subbed our t back in. So plugging this back in, we get u is cosine t, so it's going to be 2 cosine cubed t over 3, going from 0 to pi over 2. All right, and so that's going to give us minus 2/3. So the work is going to be minus 2/3 there, the work done by the force field on the particle along the quarter circle. All right, so just a brief note. So if we went in the opposite direction along our curve, note that the line integral in the opposite direction of f dot dr is going to be equal to the negative line integral going in the direction we were originally traveling. So in this case, if we were going to travel the other direction along the line integral, then we would have, it would be positive 2/3 traveling in the other direction. All right, so that is it for this part of the lecture. I would like you on your own to try out problems 23 to 26 in the section of your textbook, and 31 to 35. I have posted the problems on Moodle so that you can actually look at them in case you don't have access to the textbook right now. And I have also posted the solutions, so go through those very carefully. All right, so I will see you next time.